Okay, as you all know, we are now kind of moving into the textbooks. We're shifting gears a little bit in class, moving away from the reinvention exercises and now kind of reading through the textbook. You all probably know, you're math students, you've been in a bunch of classes. Textbooks aren't always the easiest things to read. There's kind of an art to reading a textbook. And one thing about reading a book or any math book is that you kind of have to actively read it. You can't passively read it like you're going to read a novel or an article on the internet or something like that. You have to actively read it. And what does that mean? That means you read it with a pencil in hand, and you kind of try to fill in the gaps. And if you see things that are confusing, you try to rewrite them or rework them in your own writing. There's going to be some times that I'm going to ask you to do that explicitly. So, in fact, today I'm going to ask you to rewrite a proof at some point. So there you go. But one thing that you should definitely do, since we're now in section 1, before tomorrow, you should spend some time with chapter 1 of the book. So at some point, you should sit down with chapter 1 and read it. And as you do, pay close attention to 1.2 and 1.3, because those are the two sections that we're really spending the most time on today. So read through those, look at the definitions, look at the theorems, make sure that they're making sense. And as I talk today, I'm going to go through some of the theorems, and I'm going to sketch out proofs, but I'm not going to go through every line of the proof because the proofs are available to you in the textbook. But what I want to do is I want to equip you to understand what the textbook is writing down, which is not always completely natural. As we shift into kind of this new phase in the class, expect our videos to be a little bit longer. And as part of that today, I'm actually going to do it in 2 videos. So I'm going to put 2 pieces together to make our video. And I'll probably do more of that as we go on. Okay, so the first thing is we read section 1.2. I kind of want to just talk a little bit about axioms. And you all have probably been through and talked about some of this stuff already in class. In other classes and in other math places. But I just want to give you a little bit about how I think about mathematics. And that is, when I think of the world of mathematics, I think of it as kind of being built on axioms. And then in some ways, definitions are somewhat like axioms. Definitions are what we use to make our axioms come to life. But what is an axiom? Well, an axiom is something in the middle of mathematics that we just have to assume is true. It's like the very core basic principles. And so axioms are really pretty simple things. So for example, if you go to set theory, one of the axioms is that there exists an empty set. This is not something you prove. This is not something that you go try to establish out of something else. This is just a starting point. So you start with this set. And then you say things about unions and intersections of sets. Well, it turns out we have axioms for the real numbers. But as I think about mathematics, I kind of think of it in almost this Lego sense. And that is that we have an axiom here, and then maybe I have another axiom here. And these axioms are like our building blocks. And then what happens is, once we know those axioms, well, then we can prove some sort of theorem based on those axioms. And so maybe those 2 axioms combine to give you some sort of theorem, and maybe these axioms combine to give you another theorem. And then, well, maybe you can use those 2 theorems in combination to build a new theorem. And maybe somewhere along the way, these theorems or this axiom inspires you to write a definition of something like we've done in class a few days. And then you use this theorem over here and this new definition that you created to create even another theorem. And what happens in this way is we kind of go about building the world of mathematics. And so these axioms are the cornerstones that we build on. It turns out that the axioms are super important. How you choose them is essential. And there's a really interesting note on axioms that's going to come kind of in 1.6. So I'm not going to talk about 1.6 today. Instead, I'm going to give you kind of a video watching assignment over the weekend that I'll have you watch a couple of videos that I think are kind of interesting about 1.6, and then kind of report on what they say. But at any rate, as we think about axioms, one of the important things is we're trying to define the real numbers, but it turns out that axioms build up all of our numbers. And so the axioms that we use to describe the integers are slightly different than the axioms that describe the rational numbers and are different than the axioms that describe the real numbers. And so what we're trying to do today is to describe the real numbers. But let's just think for a moment before we move on. What are our most common sets of numbers? So the most simple set is the set of natural numbers, and this is the set we're probably all familiar with. And this is the set we've been using over and over again, and it's 1, 2, 3, just like that. These sets are sometimes called the counting numbers, or something like that, because we just start at 1 and we move on. The next set that we often speak out is what we call the whole numbers, which I use a W to abbreviate. And what is the whole numbers? The whole numbers are the same set as the counting numbers, except we add that number 0 into it. So that's the only difference between the whole numbers and the integers. And okay, so we're moving up the chain here. We now have the integers, or we now have the natural numbers and the whole numbers. What's our next level? Our next level is the integers, and we use a Z to represent the integers. And what do we mean by integers? Well, integers, we throw in this mix our negative numbers. So now we go, not only do the numbers count forever in the positive direction, they count forever in the negative direction. So we've added negative numbers into the mix. Okay, let me come over here to the side, and then if we're going ever larger, probably the next set that we would talk about is the rational numbers, and we use a Q to define our rational numbers. And what are the rational numbers? Well, the rational numbers are every number that can be written as n over n, where n and m are integers, and m is not 0. Okay, so that's our set of rational numbers. And then finally, we get our set of real numbers. And the real numbers are a little bit less clear. And so what is it that makes the real numbers different? Well, we know that there are rational numbers there are real numbers that are not rational numbers, like pi or the square root of 2. And those are actually really interesting proofs to go through. But what is the distinguishing characteristic? And in a sense, that's kind of one thing that I really want you to think about and that I want to talk about today. And that is, as we go through these, I like to kind of draw a little picture. And that is, I think of my natural numbers as kind of sitting here in the middle. And then within those natural numbers is a larger set that contains the whole numbers. Within that is a larger set that contains our integers. Within that is a larger set, and here I'm going to erase my real numbers here. Within that is an even larger set that contains all of our rational numbers. And then finally, we have the largest set that we're going to talk about this semester, and that is the set that includes the real numbers in it. And so we'll come back in just a second, and we'll say, what's the difference between these? Well, one thing we know about real numbers is that they're kind of decimals. So these are, so numbers that are like, if these are decimal places, then point C, D, E, and they can go on forever. So, but this isn't a real good description, right? All these other descriptions are much more clear and precise, but real numbers are numbers that have decimal representations. So let's move on through. So thinking about these axioms, I want you to think a little bit more careful about that as we move forward. So as we think of our real numbers are defined by axioms, and we have a whole bunch of these things. By the way, these are all the things that you saw back in the transitions to proof class. So when you read through chapter 2, what you'll see a lot of theorems, a lot of definitions and axioms that all come from the transitions class. So I'm not going to spend just a ton of time on that because I'm assuming that you've had that class. I know that just because you've taken a class doesn't mean you're a master of all of it, but I don't want to spend just an outrageous amount of time reliving that class. You can go find your notes or some other things to relive that class, or come see me in my office hours. I'm happy to help you. I'm just not going to spend the time right now on this video. But let's just say a few things about what are these axioms and what do the words mean. Well, the closure axiom says that if you say add two real numbers, that you get a real number back. Or similarly, if you multiply two numbers, you get a real number back. Associative property says that if you add, it doesn't matter how you put these parentheses on there. I should have, let's see. So the associative property says that if you add, it doesn't matter how you put the parentheses on there. You can group the a plus b first, or you can group the b plus c first, and you get the same result either way. And similarly, we have an associative property for multiplication. Commutative property just means that it doesn't matter the order in which we write things. So if we add a first to b, or we add b to a, we get the same result. Or similarly, if you multiply a first or multiply b first, you get the same result. So commutative property says these things don't matter. It actually matters that we talk about these properties because there are things in the world that are not commutative. For example, matrices. So whenever you go through linear algebra and you multiply matrices, you find that those are not commutative. So this just can't be taken for granted. But for real numbers, it definitely always works. Distributive property, we know what that means. A times b plus c equals ab plus ac. And finally, we have our identities. Our additive identity is that we have 0, and 0 is the unique number that when you add it to a, you get a back. Actually, you add it to any number and you get it back. And similarly, the multiplicative identity is 1, and so when you multiply by 1, you get the same number back. Similarly, we have inverses, and that is the number that you need to give us these identities. And so we have all these axiom properties, and look through 1.2. You'll be reminded they're said a little bit more completely than I said here, and also there's all the theorems that you did in transitions. So go back, remember transitions class, remember how we proved all sorts of interesting things from these theorems. Things like 1 is not equal to 0, or things like. Actually, I think that's usually an axiom that we include. Okay. Once we have these that we call our field axioms. Okay. So let's think about these field axioms. So as I look at these axioms actually tell us what the differences are that I was going for just a minute ago between the natural, the whole, the integers. So if you think about it from this perspective, we might notice something like this, that our natural numbers, well, those are kind of the counting numbers, the most natural things. As we move from the natural numbers to the whole numbers, what have we done? Well, the only thing we've added is a 0. But 0 isn't just some random number to add. 0 is an important number because it fits a property. What property does it fit? It fits this identity property. So what we've done is we've included an additive identity. So that's what we've added to the world of mathematics by moving from the natural numbers to the whole numbers. So it's like we've added an axiom. So as I look through here, the natural numbers are closed, they're associative, they're commutative, they're distributive, but they don't have these inverse and identity laws. So in order to add this one identity law, we needed to move from the natural numbers to the whole numbers. Now similarly, when we move from the whole numbers to the integers, what did we add? Well, we added all these negative values. And so what are the negative values giving us? The negative values are giving us inverses now. So we started with just our set of natural numbers, which have all the basic properties. We now added the identity, and that gave us the whole number. And now we add additive inverses, and that moves us into the integers. Okay, and then finally, we move over here to the rational numbers. And what do we do when we try to go from the integers to the rational numbers? Well, what we're now adding is this ability to divide. But what is division really? Division really is this multiplicative inverse property. So what we've really done is we've added the multiplicative inverse property. So what you can see, and this is how I think about these different sets of numbers, that as we move through the numbers, what we've done is we've added properties, we've added axioms, and these axioms together build more and more complicated numbers. So what I want you to ask is, what is the property that we've added when we've gone from the real rational numbers to the real numbers? And let me say, it's not obvious. It's not any of these properties that we've listed here. It's not one that you generally talk about in something like a transitions class. So think about it just for a second. What is the property of numbers that makes real numbers different from rational numbers? What's true for all real numbers that's not true for all rational numbers? Think about that and make that your first task. So try to respond to that question and write it out. And you could look it up, but don't do that. Instead, just use your best thought process to come up with that. Okay. Once we've got our axioms, we're ready to talk about order axioms. And when we say order, we're really just talking about things that have a less than or a less than or equal to, but we'll stick with less than. The trichotomy property, you see the word tri here, that's 3. And that just means that every number is either greater than 0, less than 0, or equal to 0. So, and then if I had two numbers, they're either greater, less than, or equal. You can't be both greater and less than 0 at the same time. So every number fits into exactly one of those. Similarly, we have this transitive property that if A is less than B and B is less than C, then A is less than C. You're familiar with this. We use the transitive property all the time. People like to use the transitive property in sports, right? If team A loses to team B and team B loses to team C, then that means A would lose to C. But in sports, this is absolutely not true. The transitive property fails all the time. Okay, so in case you're curious. Finally, we have things like the additive property, which says that if A is less than B, then A plus C is less than B plus C. And this is always true, no matter what that C is. And then finally, the multiplicative property, which is a little bit trickier, because if A is less than B, then A times C is less than B times C. Well, this is true if C is a positive number. However, if C is a negative number, then we know that that inequality switches directions. We know that switches directions. Okay, again, these are just our axioms. This is things we saw in transitions class, so I don't want to just really overwhelm ourselves with that. I do want to spend a moment on absolute values, and the reason is, as we've already seen in this semester, absolute values, even though you spent time on it in transitions, absolute values are just really a critical part of this course, and they show up over and over and over again. So as we think about absolute value, the way a book defines absolute value is often like this. The absolute value of A is A if A is greater than 0, and negative A if A is less than 0. And this is a perfectly valid definition. In fact, this is probably the best definition. We need an equal sign, so let's include the equal sign on the greater. And this is a perfectly valid definition. It's probably the best definition for us to use. But this kind of in some ways lends us back to thinking about absolute value the way you might in a high school or junior high class, where what absolute value signs are, they just change negative signs to positive signs. And although that's true, I think there's a little bit of a richer way to think about absolute value, and I think that richer way is thinking of absolute value in terms of a number line. And so if I have a number line and we have 0 right in here in the middle, then what is the absolute value of A? Well, if A is over here, then the absolute value of A, then the absolute value of A is just whatever that distance is between 0 and A. Similarly, if we had a negative value over here, then the absolute value is, again, just whatever that distance is. So we could think of absolute value in terms of distances. And this actually works really nice because you'll notice absolute value is also the notation whenever we're in a three-dimensional class and you have a vector v. We often will talk about the magnitude of v. And what are we talking about? Well, we're actually talking about that distance from the origin out to the tip of your vector. So So when we say these absolute value signs, we probably should always have in our mind an idea of distance. And I want to notice that the idea of distance makes a lot of sense in the types of inequalities that we've been dealing with lately. So let's think of a different type of inequality. Let's think, for example, what is the inequality x minus 3 is less than 1? What is this really telling us? Well, this x minus 3 is really telling us something about the distance. But what distance is it? It's almost like it's the distance between x and 3. So if I come back to my number line picture that I had a second ago, and we've got 0, 1, 2, 3, 4, it's like x minus 3 is the distance. If x is somewhere like right here, then this distance right here is the distance x minus 3. It's if I take that magnitude and subtract x and 3 from each other, that x minus 3 absolute value is that distance. And that ends up being a really nice representation, because now, as I think about this problem, what are all the collections where x minus 3 is less than 1? Well, it's like I start at 3, and then I move 1 in this direction, and it gives me that way. And then I move 1 in that direction, and it gives me that way. And so I can see right now, without doing any work, that that this absolute value sign is the exact same as the range from 2 to 4. And to me, this is, like I said, a really nice way of thinking about what these absolute values are. And as we think about the absolute values as measuring distance, then maybe some of our definitions that we've been going from start to kind of make a little bit of sense. So we see that definition we had last time, where you had where we had x minus a is less than delta, then f of x minus L is less than epsilon. Well, that makes a little bit of sense if we think of this in terms of this distance conception. And then I draw my graph, and what we have is we have a here, and we're really talking about, when we say x minus a is less than delta, we're talking about this distance, everything that's within a distance delta of a. And similarly, when I come over here and think of this guy, what this is really saying is everything that's within a distance epsilon of L. And so that kind of gives us that picture we were talking about earlier when we interpret absolute values as distances. And I think that's really useful for us. Okay, well, this all comes out really nicely, because we have a theorem that really is useful for dealing with absolute values. And it's just this theorem that we've used several times already in this semester. But it's just that if the absolute value of a is less than some number, then what that really means is that a is between negative m and capital M. But notice if I use that on this application, then I can get the exact same answer that I got when I did it intuitively. Because that would mean negative 1 is less than x minus 3 is less than positive 1. And then I can just add a 3 to all of these sides. So I can just add 3, add 3, add 3. And then negative 1 minus 3 is 2. This is x. And 3 plus 1 is 4. And what do I see? I see that using this theorem gave me the exact same answer that I had when I kind of thought of it in terms of distance and drawing my picture. Okay, as far as absolute values are concerned, there's one last idea that we need to talk about, and that's just this idea of triangle inequalities. And so we've already mentioned one of the triangle inequalities, and that first triangle inequality is a plus b is less than or equal to the absolute value of a plus the absolute value of b. And you can probably guess we're going to use this over and over and over this semester. So, for example, if we have some expression that looks like x squared minus 3x, a really common thing to do, or maybe a first thing to try if we're trying to simplify this, is, well, let's just compare this to x squared plus negative 3x, and then ask, well, how big are these numbers? And then we might be able to bound it by some other number, and hopefully we get epsilon over here in the end when we eventually get down in. Okay, but but we can see that is this was our theorem, but how would we go about proving that theorem? Well, you could prove the theorem by cases and just say when A is positive and B is positive and A is negative and B is negative, and kind of look at all those different cases. But one really slick way to do it is to recognize that A has to always be has to always be less than or equal to the absolute value of A, because if it's positive, they're equal, and if A is negative, then they're less. But it's also got to be greater than or equal to negative the absolute value of A. So convince yourself of this, that A is between positive and negative the absolute value of itself. Similarly, B is always between positive and negative the absolute value of itself. Now, if you look really closely, what you'll see is that we can take these two lines and just add them together, and then we get the inequality that we want. So we've got negative A minus B is less than or equal to A minus B, or A plus B, my absolute value of A plus the absolute value of B. And this side over here, if I factor out my negative sign, is just negative absolute value of A plus B. And now, this is just our absolute value symbol. So this means the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. So this is just comes to that theorem where we had that theorem that I wrote earlier, that negative M is less than A is less than M is the same thing as saying the absolute value of A is less than M. So think of this part as the A and this part as the M, and maybe it all starts to make sense. Okay, so that's a really nice theorem that we need to be pretty familiar with. But it turns out there's also a second version of the triangle inequality that we're a little less familiar with. So let's that's interesting. So that we're a little less familiar with. So let's mark it down and kind of think about it for a second. And it is this version, and it says the absolute value of A minus the absolute value of B is less than or equal to the absolute value of A minus B. So this is basically saying, what do we do with an inequality when we have subtract signs? Well, if you have subtract signs, one thing you can do is you can just use your traditional one, but use it as plus and negative. But sometimes that's not useful. And in fact, if you're trying to go the other direction, so notice this triangle inequality is really useful for going that way, whereas this triangle inequality is more useful for going that way. So if we have an absolute value of A minus B, you can show that it's greater than something, and so you can start moving the other direction in your proof. Although don't be too rigid with that. I mean, there are times when you want to do both of these in both directions. How would I prove a theorem like this? It's actually not the hardest thing that we'll ever do. All it really takes is it just takes thinking. It takes just a quick observation, and that is that the absolute value of A is the same as the absolute value of A minus B plus B, and then we use this theorem right here to, and we use this theorem. Sorry, you probably hear my cat going crazy. And then we use this theorem right here to say that the absolute value of A is less than or equal to the absolute value of A minus B plus the absolute value of B. Now, simplify a little bit. Let's just subtract that absolute value of B from both sides. And then we get the absolute value of A minus the absolute value of B is less than or equal to A minus B. Okay, well, if we did the exact same thing with the absolute value of B equaling to the absolute value of B minus A plus A, we would get, we could do the exact same work, and what we would get is we would have that negative the absolute value of A minus the absolute value of B is less than or equal to, and in this case, sorry, this should be an absolute value over here, is less than or equal to the absolute value of A minus B. So let's make sure this works out. So this is B minus A, and then and this is so sorry. So this is negative A negative a minus b. This is one of those cases where, just like a textbook, maybe you should work the details out yourself. So maybe you should look at these 3 dots here and say what needs to go in. Well, what you need to do is split up your absolute values using your theorem, move your a over, and you would get b minus a, but then factor out a negative sign to switch it, to make them positive. And then we see now that these things all combine together. And so if I combine this piece and this piece, we've got negative the absolute value of a minus the absolute value of b is less than or equal to a minus b is less than or equal to a plus b, not plus, a minus b, and then that gives us our theorem. So just like earlier, we have our middle part, and then we have our 2 outside parts. Okay, so there are a few proofs. These are proofs that probably should have kind of been somewhere in your transitions course, and you've seen them before. But that being said, I hope that this kind of refreshed a little bit of your thinking. But the real nice thing about absolute values is once we've made all this progress, we can really start to tackle some problems and simplify some things like we did in class today. So one thing I want you to do is do a little bit of practicing with your absolute values. So I want you to start with this absolute value right here. So start with x minus 3 is less than 1, and use that to do whatever you think the best approximation of x times x minus 1 is that you can come up with. So make your best possible approximation of x times x minus 1, given that x minus 3 is less than 1. And then once you've done that, see if you can prove this theorem. So here's the theorem that we have. If x is less than y minus epsilon for all epsilon, then x is less than or equal to y. This is a really good theorem because this kind of is at the heart of what we've been doing all along, right? So what this says is that if you have a y right here, if you have a number line and we put y on it, and then we add some just really small amount, epsilon amount, and take y plus epsilon. Well, if x is always found on this side, so x is always found on this side, well, if this is true for all epsilon, then what you can do is you can kind of imagine in your mind, right? You can kind of imagine in your mind these epsilons moving back here and getting closer and closer and closer. So the only possibility is for x to be somewhere between y and less. So it's impossible for x to be bigger than y. But see if you can prove this. The textbook has a proof, but try your own. I might suggest that you start with a proof by contradiction. Okay, as I said, the videos are going to be a little bit longer. We've got a little bit more to talk about. I'm going to do a second video kind of focusing on 1.3 in just a little bit. But try those 2 tasks, try this video, and I'll